Hi, I thought I'd start by showing you this picture. It's not the most scenic of places. It's a bit grubby, a bit abandoned, a bit forgotten. Does make you wonder where it is. And also, why is it so important that I'm starting uh, this lesson by showing it to you? Admittedly, this photograph is now a good few years old. Let me show you a more recent picture of the same site. This is the London Olympic Park, home to the 2012 London Olympics. The reason this Olympic Park was built in the east end of London was the fact that the site that it's built on was one of the largest sort of open and areas available for development in the city. The reason it was still open was that this land was fairly horrifically contaminated. The work done before any building was done on this site was largely trying to clean up the uh, pollution from past industry that was that contaminated the soil and the land underneath this site to a really quite high degree. And a good chunk of the budget for the London Olympics was to sort this pollution out and to be able to regenerate this site to allow it to be used. This lesson is all about contaminated land, how it gets contaminated, and some of the remedial measures that can be done. It is an aspect of geology that does employ a lot of geologists, including ex-students from this school. Okay, let's go. If we think about contaminated land, really we need to be looking at um, two things that get contaminated. We have groundwater and also the soil. Now, the main sources of pollution are industry, agriculture, domestic waste from landfill sites, for example, and urban areas in general, and some of the spillages and accidents, I suppose, that happen uh, in an urban area. The materials that can go into the ground and contaminate it are very broad. Pesticides, fertilizers, sewage, leachate, petroleum, chemicals, all sorts of different materials, each of which will pose its own particular hazards. Now, areas have different vulnerabilities to this contamination. In particular, where we have unconfined aquifers. So we have permeable rock at the surface with maybe a shallow water table beneath it that's then has high permeability because they're often used as aquifers, but they're also the ones that where pollution can get most quickly into that and most easily into that groundwater and spread the furthest. Areas with lower vulnerability have an impermeable protection on top of it, the confined aquifer, maybe where the water table is a bit deeper as well. They're going to be much less vulnerable to contamination. Just to give you some examples here, this is the southwest of England, and it shows you areas shaded in red there where aquifers are vulnerable to contamination. And this isn't necessarily in terms of the human activity that's on top of it, this is down to the geology. What's the geology of these aquifers that makes them vulnerable to any contamination that might occur above them. Now, when we look at this contamination, we look at what we call a three-zone model. These area around a borehole where there is extraction of water going on. Zone 3 is the whole catchment area of the borehole, wherever water goes from the rocks into that borehole. Zone 2 is the 400-day travel time. So how long it takes water, the distance to the borehole where water will travel within 400 days. Or that could be 25% of the catchment area, whichever of those is bigger. Clearly, if there's contamination in zone 2, that's a bigger deal than any contamination in zone 3. Zone 1, then, is the area around the borehole where the water will take up to 50 days to travel to the borehole. Because if there's contamination within that, any bacteria, for example, say if it's sewage, we'd expect it to perhaps to die within 50 days. So these zones of vulnerability can determine the amount of protection that needs to take place. Now, industrial chemicals are a particular problem. These materials are create different hazards depending on obviously the nature of the material, but also their solubility. So if you get soluble chemicals, they're going to spread throughout the groundwater. If you have ones that are less soluble, they sometimes are referred to as NaPLs, non-aqueous phase liquids. These are ones perhaps that don't mix so easily with the groundwater. So light ones, oil for example, less dense than water, that will sit on top of a water table. The heavier NaPLs, a lot of industrial solvents, for example, that are denser than the water will sink down to the bottom of the aquifer. So the behaviour of these will depend on the solubility and also the density. It is easier to deal with the light NaPLs. Because they sit on top of the water table, they're going to be shallower. It might be easier to try and extract those from the aquifer. Dense ones, though, are much harder to deal with. They go deeper, and it's much harder to get them out of the aquifer. Clearly, though, perhaps the best solution is that these things don't get into the ground in the first place. To give you an example here, this was a dense solvent that leaked from a leather factory in Cambridge. This then polluted the chalk that Cambridge sits on, which is, as we know, is an aquifer. It's very permeable, down to a depth of 50 meters, and was significant for 2 kilometers in the direction of the groundwater flow. Now, the chalk in the east of England is a crucial aquifer. It's a very dry part of the country, and a major public water supply became contaminated and unusable. So you then are faced with the problem of either the expense of treating the water to remove this solvent, or to find an alternative source of the water. Both of these are going to be really expensive. And this type of contamination won't just sort of evaporate away and disappear. There are issues particularly with petrol stations. There's lots of them. For a start, there are distribution networks of pipes. For example, a lot of aviation fuel is piped around the country to airports, um, where you get leaking tanks, fractured pipes, just spills and mistakes with filling containers, road accidents. All these can put petroleum products into the environment. There's um, a very low level of contamination that's allowed for drinking water. Um, 1 part hydrocarbon per 100 million parts of water. It doesn't take a lot uh, of hydrocarbons to contaminate a water supply, so it becomes unusable. This diagram illustrates some of the potential issues from a leak of a petrol station. And remember as well, this could be an old petrol station that's not used anymore. It might still have some petroleum products, down in the bottom of a storage tank, and may not be removed when the petrol station falls into disuse. This shows as well one of the potential solutions, where you're pumping the aquifer that's underneath that's been contaminated, to remove both water, to create a hydraulic gradient, so the water will flow towards these boreholes, and then to pump the contaminant out. This is all expensive stuff, though. We can see from this graph, this is the number of contaminants and their different sources, just what a wide range of materials that hydrogeologists might be dealing with it when they're managing contaminated land. There's a lot of different stuff to deal with, each of which will pose its own set of specific hazards. Contamination is both historic and current. If we look historically, gasworks, foundries, coking works in particular, that used to dump their waste into the ground and let them soak away, still cause problems today. More modern pollution will include things like complex chemicals. Now, they should be managed in more modern environments rather than just put into the ground and forgotten about. But there's still the potential for accidents. It's estimated over 500 square kilometres of the UK is contaminated land. To give you some idea, that's about 1.5 Vale of Glamorgans, with over 50,000 sites around the country. There are some particular places where there is a very high chance of significant contamination. Old gasworks here. This up until the late 1960s, we had public gas supplies were actually manufactured from coal. They called it town gas. Now, to do this, they cooked the coal to produce gas, but what was left was a mixture of some really, really unpleasant things, and very often these were just put into soakaways around the site, so they just supposedly disappeared. These sites in urban areas are primed for redevelopment, for building other things on. To do that, the sites need to be decontaminated. I mean, we're fortunate now to have natural gas that doesn't require this, but the legacy of this even though we haven't manufactured gas in this way for over 50 years, still exists. It's one reason it's really important to understand the history of a site before you start building on it. And certainly, here's a tip, before you buy a house on it. We see under urban areas pollution from all sorts of sources, whether that's industrial, sewage leaks, all sorts of things from cities can get into groundwater. Um, Birmingham, for example, used to have an aquifer. Well, Cardiff as well, to be honest, had aquifers underneath the city that were used for public supply. Um, those aquifers are now contaminated. So that creates a number of problems. Firstly, you can't use the water. Secondly, of course, that the groundwater levels may well be rising. Because if you have cities where groundwater has been used, depleting the water table, reducing the height of the water table, the city then builds and develops, getting used to that lower water table. With the growth of the city, though, and the contamination of its aquifer, if that pumping stops, the water level will start to rise, potentially then starting to reach some of the underground structures, underground services that those cities will have built in the meantime. So, what can we do about it? One potential solution is to try and contain it. So, if you have a point source of pollution, uh, it may be possible to dig um, a, a trench around that pollution source and to seal that in, to keep the any pollution beneath that site, to stop it spreading into the wider environment. This has been done at a landfill site down in Cardiff Bay, a place called Ferry Road. When Cardiff Bay was being redeveloped, and there was significant amounts of contaminated land there, to contain the landfill, which is now the Hill, which is the public park down in Cardiff Bay, just by the retail park. To contain that pollution, a trench was dug around the landfill site and filled with impermeable clay and cement, and that dug down into the impermeable rock underneath. Second solution is to get rid of it, to dig it out. Either pumping out the water or digging out the soil and putting that into a landfill site. It's not a cheap option. This, if you dig out lots of soil, for example, that then has to go to a landfill. That's going to be expensive, and you then need a whole set of more material, clean material, to put back in the hole. It is possible then, in some cases, to use what we call bioremediation. This is where nutrients are pumped into a soil to encourage the growth of bacteria. The bacteria then break down material, particularly organic solvents and hydrocarbons, in the soil. They break them down, convert that organic material into carbon dioxide, water, and that can then be pumped out, treated, and released into the air. But this only works where you have organic material that can be broken down by bacteria. Bioventing gets rid of what we call the volatile content. This is the stuff that will turn to gas that smells. So particularly with things like hydrocarbons, and it's really just pushing air into the contaminated soil, getting that hydrocarbon to turn into a gas, and then pumping it out. For some pollutants, particularly things like heavy metals, but other ones as well. You will get plants that will take up those heavy metals. Um, this is a nice way of doing things, clean, efficient, inexpensive, um, but it's a slow process. Getting the plant to remove the pollutant uh, into its body, and then being able to get rid of those plants in a safe and effective way. So, as we watch the sunset over the Olympic Park, it is possible to remediate contaminated sites. However, none of it is easy, and certainly none of it is cheap. It's why modern industries will spend a lot of time and effort to minimize or eliminate the risk of environmental pollution. We have a principle today of polluter pays. So the expense of remediating any pollution is going to be far greater than any saving made by not putting the protective measures in place. But accidents still happen, and we still have the legacy of 150 years of industrialization. It's always worth checking what a site has been used for in the past.